Midnight approaches on the 24th of July, 1943. In a dimly lit underground facility on Hamburg's northern edge, a young German radar technician prepares for another shift. His name is Klaus Hoffmann, 23 years old, trained at the Luftwaffe's Specialized Signals Academy. For nearly a year, he has watched the rhythmic patterns of British bomber formations crossing into German airspace, guiding defensive fighters toward their targets with practiced precision. The equipment before him represents the cutting edge of military technology. Germany has invested enormous resources into constructing an elaborate defensive network stretching across northern Europe, billions of Reichsmarks worth of radar stations, each staffed by highly trained operators who can read the glowing displays as fluently as others read printed text. Hoffmann adjusts the controls on his Würzburg radar unit, watching the familiar phosphorescent glow of the cathode ray screen. He knows this equipment intimately, every knob, every dial, every characteristic pattern the display produces. He has logged over 700 operational hours, tracking countless aircraft through the darkness above Germany's second most important city. Just before 1 o'clock in the morning, the early warning systems detect an approaching bomber stream. Range 113 kilometers, bearing north-northwest. This is standard procedure. Hoffmann's hands move efficiently across his controls. Track the formations, coordinate with searchlight batteries, direct the night fighters toward their targets. Win another engagement in the ongoing battle for control of German skies. But 23 minutes past 1, something unprecedented occurs. Hoffmann's display suddenly erupts with returns, not the clean, distinct echoes he has learned to interpret with such accuracy, but thousands upon thousands of signals. His screen transforms from a precise tactical instrument into a solid mass of light. Every direction shows contacts, every range, every altitude. The carefully organized defensive grid dissolves into electronic chaos. His hands freeze. Behind him, 3 other operators face identical displays, all showing the same impossible phenomenon. Their watch commander stands motionless, staring at the screens in disbelief. For several seconds, nobody speaks. The fundamental technology upon which Germany's entire night defense depends has become, in an instant, completely ineffective. What Hoffmann cannot yet comprehend, what none of the 200 radar operators across Hamburg's defensive perimeter can grasp in this moment, is that they are witnessing not equipment failure but a weapon. A countermeasure so elegantly simple that British scientists feared deploying it for over 12 months. It has just rendered billions of Reichsmarks worth of sophisticated electronics functionally useless. To understand the magnitude of what happened in that underground facility, we must first examine what German air defense had become by the summer of 1943. The system stretched from Denmark through northern Germany, across the Netherlands and Belgium into northern France. A chain of overlapping radar zones, each approximately 32 kilometers from north to south and 20 kilometers east to west. The British called these defensive sectors boxes. The Germans named them Himmelbett zones, literally 4-poster bed zones, because of their arrangement on tactical maps. Each zone contained precisely coordinated equipment. First, a Freya early warning radar with maximum detection range of 160 kilometers, operating at a wavelength of approximately 2.5 meters. It could detect approaching formations at long distances, but could not determine altitude with precision. Once the Freya acquired a target and established approximate position, 2 Würzburg tracking radars took over. The Würzburg represented the backbone of German radar capability. Operating at 53 centimeter wavelength in the ultra-high frequency band, it employed a 3-meter parabolic dish antenna. The system had been operational since May 1940, and by this point, approximately 4,000 units of various models had been produced. The accuracy was extraordinary for its era. Range precision within 25 meters, angular accuracy of approximately 0.1 to 0.2 degrees. This precision enabled ground controllers to guide night fighters to within visual range of enemy bombers, even on the darkest nights. One Würzburg would lock onto an incoming bomber. The second would track the assigned night fighter. A ground controller watching both plots would radio precise instructions to the fighter pilot. Hamburg, as Germany's second largest city and most vital port, was protected by 15 separate defensive zones. 9 night fighter bases operated in the immediate area, 56 heavy anti-aircraft batteries and 36 light flak batteries defended the city. Searchlight companies contained hundreds of individual lights, many radar-directed. The entire system represented enormous investment, thousands of skilled operators, and 2 years of tactical refinement. The men operating this system had been trained to trust its effectiveness completely. Radar schools transformed recruits into technicians who could interpret the phosphorescent traces on their screens as clearly as navigators read charts. They learned to distinguish between single aircraft and formations. They learned to compensate for atmospheric effects, ground clutter, the various forms of interference that nature produces. Most importantly, they learned absolute confidence in their equipment. The Würzburg had proven itself in combat repeatedly. Klaus Hoffmann was born in Bremen in April 1920. His father worked as a machinist at an aircraft factory. His scores on technical aptitude examinations qualified him for specialist training. In January 1940, he transferred to the Luftwaffe Signal School for an 8-month radar operator course. Mathematics of wave propagation, physics of radio frequency energy, electronics fundamentals. Students worked with actual equipment, learning to interpret cathode ray displays until pattern recognition became instinctive. By July 1943, Hoffmann knows the characteristic signatures of different bomber types. Lancasters produce slightly different returns than Halifaxes. Stirlings with their larger dimensions stand out distinctly. His station at Hummelbüttel is designated Hamburg Nord 4. His crew on the night of July 24th consists of 4 men. The shift begins at 2200 hours. At midnight, the Freya network reports the main bomber stream approaching. Range 90 kilometers, direction Hamburg. At 1, his display picks up the first return. Range 47 kilometers, a single aircraft flying straight and level. Hoffmann centers his tracking gate on the contact. Perfect lock. At 1, the impossible happens. His screen explodes with light. Not a gradual increase, not a growing number of contacts. A sudden total saturation, where 30 seconds earlier, his display showed a single clear return at 36 kilometers range. His screen now displays what appears to be hundreds, perhaps thousands of individual targets. Every range band from 10 kilometers to maximum detection range, every bearing. Hoffmann's first thought is equipment malfunction. The transmitter must have failed, causing the receiver to display noise as returns. But the display characteristics are wrong for transmitter failure. These are not random noise patterns. These are distinct individual echoes. Each one has the signature of a reflected radar pulse. Each represents energy that traveled from his antenna, bounced off something metallic, and returned to his receiver. He checks his indicators. Transmitter power nominal. No fault lights illuminated. The Würzburg is operating exactly as designed. This is not equipment failure. His second thought is atmospheric interference. Severe weather can create multiple false returns, but the weather tonight is clear. No rain, no thunderstorms. The Freya operators reported perfect conditions. And atmospheric returns do not look like this. They are diffuse, scattered. These returns are sharp, distinct, like aircraft. Behind him, the watch commander is on the telephone with zone headquarters. His voice carries an edge Hoffmann has never heard before. Sir, our display has become saturated with contacts. All ranges, all bearings. We cannot distinguish individual aircraft. Request instructions. On the radio, a night fighter pilot's voice comes through clearly enough for Hoffmann to hear. Ground control. What is my vector? I have no target on my airborne radar. Repeat, no contact. Where is my target? The watch commander looks to Hoffmann. Hoffmann stares at the impossible display. For 10 seconds, the only sound in the operations room is equipment hum and the faint crackle of radio static. Then reports begin flooding in from other stations. Hamburg Nord 1 display saturated. Hamburg Nord 6 cannot track individual targets. Hamburg West, radar returns covering entire display. Hamburg East unable to vector fighters. One by one, every Würzburg station around Hamburg reports identical conditions. The entire defensive network has gone blind simultaneously. At zone headquarters, the watch officer makes a decision that will echo through Luftwaffe command structures all the way to Berlin. He orders night fighters to return to base. Without radar guidance, without ability to track bombers or direct interceptions, the fighters are flying blind. They will land, refuel, and wait for the problem to resolve. Searchlight batteries, their radar-directed master lights wandering aimlessly across empty sky, switch to manual operation. Teams of 3 men operate each light now, one watching the horizon with binoculars, 2 others training the beam based on his shouted directions. It is the technology of 1918. The precision of 1943 has vanished. Flak batteries, firebox barrages, throwing up walls of explosive shells at predetermined altitudes and coordinates. Without radar to track individual aircraft, They can only fill volumes of sky with shrapnel and hope a bomber flies through it. The accuracy they developed over 2 years of radar-directed fire is gone. They are shooting at ghosts. Above Hamburg, 791 RAF bombers fly through defenses that should have destroyed 50 or 60 of them. The night fighters that manage visual contact find themselves alone in a sky full of bombers, unable to coordinate with ground control, unable to receive vectors to additional targets. The Himmelbett system, which has claimed hundreds of RAF aircraft, has ceased to function. In the underground facility at Hummelbüttel, Hoffmann continues watching his display. The mass of returns has not diminished. If anything, it has grown denser. New contacts appear constantly. The entire defensive network remains blind, and still no one can explain what happened. At 47 minutes past 1, 24 minutes after the first saturation, something changes. The southernmost edge of the contact mass begins to fade. Slowly, over 3 minutes, returns on the southern side of Hoffmann's display decrease in intensity. The solid wall of light becomes scattered points. Then the points fade. Then they disappear. For a moment, Hoffmann thinks the problem has resolved. Then he understands. The bomber stream has passed through his sector. Those returns were real aircraft masked by something creating thousands of false echoes. The bombers are now over Hamburg itself, dropping their ordnance, and he's been unable to stop any of them. The bombs fall for 90 minutes. From 100 hours until 2:30, Hamburg burns. Hoffmann can hear explosions even underground. The building above his operations room trembles with each impact. Dust filters down from the concrete ceiling. At 15 minutes past 3, the last bombers exit Hamburg's airspace. Hoffmann's display clears completely. The false returns that blinded his radar disappear as suddenly as they arrived. His Würzburg is functioning normally again. The transmitter operates at design parameters. The receiver shows its usual sensitivity. The display presents clean, empty airspace. Whatever blinded German radar stopped when the bombers left. At 4:30, the watch commander receives new orders from zone headquarters. All radar stations are to send personnel to search areas beneath the bomber routes. Find anything unusual. Collect any objects that might have caused the radar interference. Report immediately. At 600 hours, as dawn breaks over Hamburg, a technician returns from his search assignment. He carries a small cardboard box. Inside are strips of aluminum foil attached to black paper. Each strip measures approximately 27 centimeters long and 2 centimeters wide. The technician found hundreds scattered across half a kilometer area. They hang from trees. They lie in fields. They cover roads and rooftops. Hoffmann holds one of the strips up to morning light coming through the entrance. The aluminum catches the sun and gleams. It weighs almost nothing. It is impossibly simple. A piece of metal foil, nothing more. But the dimensions are not random. Hoffmann studied electromagnetic theory at the signal school. He understands what he is looking at. The length of the strip is approximately half the wavelength of the Würzburg's operating frequency. A perfect dipole antenna. When radar energy hits it, the strip resonates at exactly the right frequency to reflect maximum return. On a radar display, one of these strips would look identical to an aircraft. Someone does the mathematics. 7,000 packages, each containing 2,200 strips, dropped from 791 bombers at the rate of 1 package per minute. 15 million pieces of aluminum foil, each one creating a radar return. It is overwhelming in its simplicity and devastating in its effectiveness. Within hours, intelligence officers arrive from Luftwaffe High Command. They photograph the strips. They measure them precisely. They calculate dimensions and confirm what Hoffmann already determined. The British cut these strips to defeat the Würzburg specifically. They know the Würzburg's operating frequency. They understand how radar detection works. They have created a countermeasure that costs almost nothing to manufacture and completely negates billions of Reichsmarks worth of radar equipment. General Josef Kammhuber, commander of Germany's night fighter forces, will later state in interrogation after the war that the whole defense was blinded in one stroke. It is not hyperbole. In a single night, the defensive line that stretches from Denmark to France has been defeated by strips of aluminum foil. By 800 hours on July 25th, statistics begin arriving at zone headquarters. Of 791 RAF bombers that attacked Hamburg, only 12 were lost, a loss rate of 1.5%. On a typical raid, Hamburg's defenses would have destroyed 40 to 50 bombers, a loss rate of 5 to 7%. The difference represents 350 to 400 British airmen who lived because German radar was blinded. The bombing destroyed approximately 16,000 buildings. 3,000 people were killed. 120,000 made homeless. The Blohm and Voss shipyard was heavily damaged. The Kluckner aero engine factory was hit. Several U-boats under construction were destroyed. Hamburg's electrical grid sustained significant damage. And this is only the first night. The British will return. They will use these aluminum strips again. German radar operators will sit at their displays watching the same impossible saturation, unable to track targets, unable to vector fighters, unable to defend their homeland. Hoffmann stands in the entrance to his radar station as the sun rises over Hamburg. Smoke columns rise from dozens of fires across the city. The morning sky, which should be blue, is grey with ash. He can see damaged buildings from his position north of the city. He holds one of the aluminum strips in his hand. 8 months of training, 700 hours of operational experience, 2 years of successful interceptions and tactical victories, all of it rendered meaningless by this piece of metal foil. The scale of disaster becomes clear over following days. RAF Bomber Command returns to Hamburg on July 27th. 777 aircraft. The aluminum strips deployed again. German radar blinded again. This time, conditions in the city create a firestorm. Temperatures reach 800 degrees Celsius. Winds reach 240 kilometers per hour. Approximately 20,000 people die in a single night. It is the most lethal bombing raid in European history to that point. The Luftwaffe responds with desperate measures. A commander named Hajo Hermann develops a tactic called wilde Sau, wild boar. Single-seat day fighters patrol above burning cities and attack bombers visually against the flames below. It is primitive. It is dangerous. It represents complete abandonment of the radar-directed precision that defined German air defense. Engineers at Telefunken begin emergency development of countermeasure systems, modifications that would allow operators to distinguish real targets from chaff returns by measuring slight differences in signal characteristics. But development takes months. In the meantime, German radar operators sit at displays they can no longer trust. By August 1943, just weeks after the Hamburg raids, 45% of all German fighter aircraft have been relocated from combat fronts to home defense. The strategic bomber offensive is forcing Germany to divert resources from the war in Russia, from the Mediterranean, from every theatre where the Luftwaffe operates. The reallocation of industrial production to home defense becomes one of the unintended consequences of this operation. Albert Speer, Reich Minister for Armaments and War Production, will later tell interrogators it was quite a surprise when the first Hamburg raid took place, because the Allies used some new device preventing anti-aircraft guns from finding bombers. He states that he told a meeting of the Air Ministry that if this success were repeated on 4 or 5 other German towns, Germany would collapse. They do not collapse, but they never recover their confidence either. A curious fact emerges after the war that makes the defeat even more bitter. German scientists had known about this countermeasure since 1940. They developed their own version called Dupel. They tested it. They confirmed it would blind enemy radar. And they deliberately did not use it because they feared the British would copy it and use it against German cities. For over a year, both sides possess the same weapon. Both sides understand its effectiveness. Both sides refuse to use it for the same reason. Until July 24, 1943, when Air Chief Marshal Arthur Harris decides the time has come. The British deploy their version. The Germans discover that the British had the same idea they deliberately suppressed. The irony is not lost on anyone. 6 weeks after Hamburg, on the night of October 7th to 8th, the Luftwaffe drops Dupel over London. German bombers attempt to resume raids on British cities. Their radar jamming strips cut to 80 centimetres by 1.9 centimetres, precisely calculated for British radar frequencies. But by then, the strategic situation has changed. The Luftwaffe has too few bombers. The RAF has too many fighters. The mini-blitz between February and May 1944 achieves little. The technological advantage has shifted. The side with more industrial capacity, more resources, more ability to adapt will prevail. The Germans built a sophisticated defensive network, assuming their radar superiority would be permanent. The British developed a countermeasure so simple it could be manufactured in any factory with aluminum and paper. Complexity was defeated by simplicity. Klaus Hoffmann remains at his radar station for another 8 months. He continues operating his Würzburg. He watches his displays fill with chaff returns on every raid. He tracks bombers when he can through gaps in the jamming, using techniques that are more art than science. The precision of 1943 never returns. The response from German engineers comes with remarkable speed, though the damage has already been done. Within weeks of the Hamburg raids, Telefunken begins developing modifications to the Würzburg system, specifically designed to counter the aluminum strips. The first of these countermeasures operates on the principle of Doppler shift. When radar energy reflects from a moving object, the frequency of the returned signal shifts slightly. Aircraft moving at 300 to 400 km per hour produce measurable Doppler shifts. Strips of aluminum foil falling slowly through the air at perhaps 10 to 20 km per hour produce almost no shift. By adding circuitry that compares the frequency of transmitted pulses with the frequency of returned echoes, operators can theoretically distinguish between real bombers and chaff. The modification requires adding a stable oscillator to lock transmitter frequency, ensuring coherent phase between pulses. Additional filtering circuits analyze return signals for Doppler characteristics. The display is modified to highlight returns showing significant frequency shifts while suppressing those that do not. In theory, chaff returns fade into background, while aircraft stand out clearly. In practice, implementation proves difficult. The modification reduces the Würzburg's effective range by approximately 30%. The circuitry is complex and prone to malfunction. Only a handful of specially trained operators can use the system effectively. But by November 1943, approximately 1,500 Würzburg sets have been modified with improved versions. It is not a complete solution, but it restores some capability. A second countermeasure takes a different approach, using mechanical propeller modulators to distinguish between different types of returns based on pattern of reflected signal. Chaff strips tumbling randomly through air produce chaotic return patterns. Aircraft with their stable orientation and solid metal structures produce more consistent returns. Again, the modification is tricky. Few operators master it, but those who do can see through jamming with reasonable effectiveness. The Germans also attack the problem from another direction. If existing radar frequencies are compromised, develop new frequencies. The Würzburg's frequency band is expanded from its original 10 MHz width to over 100 MHz. Multiple bands are introduced. A modification introduced in summer 1944 allows rapid switching between frequency bands. If the British cut chaff to jam one frequency, operators can switch to another. For airborne radar, the solution is a new system operating at much lower frequencies around 90 MHz in the very high frequency band. Chaff cut to defeat Würzburg is the wrong length to affect this new system. The system is immune to chaff, at least temporarily, but it has problems. Its minimum detection range is initially 900 meters, far too long for night fighting. Aircraft need to retain their old equipment alongside the new, creating arrays of antennas on fighter noses that reduce aircraft speed by up to 50 km per hour. By early 1944, improved versions reduce the minimum range problem, allowing removal of old equipment. But by then, the Allies have captured an intact system when a night fighter accidentally lands at an RAF base in July 1944. Within weeks, Allied jammers are targeting the new system specifically. It is a technological arms race with no finish line. Every German countermeasure prompts an Allied countermeasure. The British develop carpet jammers to blind radars with broad spectrum noise. The Germans modify equipment to operate on multiple frequencies. The British add frequency-agile jammers. The Germans develop centimetric radar. The British capture it and jam it. The fundamental strategic balance has shifted. Germany, with its limited industrial capacity devoted increasingly to replacing losses, cannot match the pace of Allied electronic warfare development. Every modification consumes resources. Every new radar system requires factory time that could have gone to producing fighters or tanks. Every trained radar operator diverted to learning new countermeasure techniques is one less pilot, one less gunner, one less soldier at the front. For the men who operate German radar systems, the months following Hamburg bring a different kind of warfare. They sit at their displays, knowing the technology they depend on could be rendered useless at any moment. The confidence that defined their work disappears. Every raid becomes an exercise in adaptation and improvisation. Klaus Hoffmann remains at his radar station until April 1944. In those 9 months, he tracks hundreds of raids. Some nights, the modifications allow him to see through the jamming and vector fighters successfully. Other nights, his screen becomes the same impossible mass of returns he witnessed on July 24th. There is no consistency, no reliable procedure. Each raid is different. The psychological toll extends beyond individual operators. The entire German air defense system was built on the premise of technological superiority. The defensive line, the carefully coordinated network of radar stations and fighter bases, all of it assumed German radar would maintain its advantage. When that assumption proves false, the entire doctrinal structure becomes questionable. By August 1943, less than a month after Hamburg, 45% of all German fighter aircraft have been pulled from combat theatres and reassigned to homeland defence. Fighters desperately needed on the Eastern Front in the Mediterranean in France are instead patrolling German cities. The strategic bomber offensive is achieving one of its primary objectives, forcing Germany to divert resources from offensive operations to defensive ones. The numbers tell the story with brutal clarity. In 1942, RAF Bomber Command flew approximately 48,000 sorties against German targets and lost approximately 1,600 aircraft, a loss rate of 3.3%. In the second half of 1943, after introduction of the aluminum strips, Bomber Command flew approximately 60,000 sorties and lost approximately 1,500 aircraft, a loss rate of 2.5%. The offensive was intensifying while losses were decreasing. The reallocation of German industrial production has cascading effects. Anti-aircraft guns in Germany increased by 25% in the months following Hamburg. These guns require crews. By late in the war, anti-aircraft units in Germany employ hundreds of thousands of personnel and consume 25% of all ammunition produced by German industry. Every anti-aircraft gun crew member is a person who could have been fighting at the front. Every shell fired at bombers is a shell not available for ground combat. The bombing campaign's effectiveness in destroying industrial capacity is debated by historians. Many factories are dispersed, production continues, and German fighter production actually increases in 1943 despite the raids. But the diversion of resources to air defense is undeniable. Germany is fighting a multi-front war with finite industrial capacity. Every ton of steel devoted to flak towers is steel not available for tanks. Every trained mechanic maintaining radar equipment is not maintaining vehicles in Russia. The psychological impact on German civilians is harder to quantify, but equally significant. After Hamburg, approximately 1 million people evacuate the city. 60% of housing stock is destroyed or damaged. The city's labor force is reduced by 10%. Other cities watch and understand they could be next. The sense of invulnerability that radar-directed defenses provided evaporates. Albert Speer's statement to interrogators after the war remains chilling in its implications. He told Hitler's inner circle that 4 or 5 more attacks like Hamburg would lead to collapse. They did not collapse. But the fact that Germany's Minister for Armaments and War Production believed such an outcome was possible reveals the psychological impact of that week in July 1943. For radar operators like Hoffmann, the experience is more personal and immediate. He was trained to believe his technology was superior. He saw it work for 2 years. Then in less than a minute, that superiority vanished. The equipment still functions, the physics still apply, but the advantage is gone, and with it went the certainty that skill and training would be enough. The war has become unpredictable in new and unsettling ways. The British have more bombers, better countermeasures, and greater industrial capacity. German operators can adapt, improvise, and occasionally succeed, but they can no longer dominate. The night of July 24, 1943, marks a turning point that extends far beyond Hamburg. It demonstrates a principle that will define warfare for the remainder of the 20th century and into the 21st. Technological advantage is temporary, and the side with greater capacity to adapt will prevail. The aluminum strips are not a sophisticated countermeasure. The physics are elementary. The manufacturing is trivial. What makes them devastating is not complexity but timing and scale. The British wait until they have overwhelming numbers of bombers, until the Luftwaffe's retaliatory capacity is diminished, until the strategic calculus favors deployment. Then they use it everywhere simultaneously. 15 million strips dropped over one city in one night. German radar operators have no time to adapt because the adaptation must happen under the worst possible conditions during an actual attack. This establishes a pattern that continues throughout the war. The Germans develop a countermeasure. The Allies overwhelm it with numbers or develop a countermeasure. The Germans introduce a new radar frequency. The Allies capture it and jam it. Back and forth, month after month. in an electronic warfare arms race where the side with more resources eventually grinds down the side with fewer. Klaus Hoffmann survives the war. Records show he is transferred from radar operations to general Luftwaffe ground duties in April 1944, possibly because his technical expertise is needed elsewhere as Germany's situation deteriorates. His ultimate fate is not recorded in available archives, but thousands of radar operators like him continue their work until the final days of the war, tracking raids they often cannot stop, operating equipment that has lost its decisive edge. The Würzburg radar itself remains in service until the end of the war. Modified versions continue to provide some capability in the hands of skilled operators using countermeasure modifications. It can still track targets through jamming, but it never regains the dominance it possessed before Hamburg. The 4,000 systems Germany produced represent billions of Reichsmarks in investment and thousands of hours of training time. The aluminum strips render that investment partially obsolete for the cost of foil and paper. After the war, captured German radar equipment is studied extensively by Allied scientists. Several Würzburg systems are taken to Britain and the United States for analysis. Ironically, some are later used for scientific research, including early radio astronomy studies. The technology that failed to stop the bombing campaign finds peaceful applications in studying the cosmos. The broader lesson of Hamburg transcends the specific technology. It speaks to the nature of war in the modern age. Technical innovation matters, but industrial capacity, resource availability, and adaptability matter more. Germany produced excellent radar systems, skilled operators, and sophisticated defensive networks. But when faced with an opponent who could produce countermeasures faster than Germany could develop countermeasures, technical excellence was not enough. There is profound irony in the mutual possession of Chaff technology. For over a year, both sides have the weapon but fear to use it. Each assumes the other does not possess it. Each worries that deploying it will reveal its secrets to the enemy. In reality, both sides have independently developed the same solution to the same problem. The decision to deploy comes down to strategic calculation, not technological discovery. The British have more bombers and less to lose. The Germans have fewer bombers and more to fear. So the British deploy first, and the Germans discover they have been sitting on the same countermeasure all along. Klaus Hoffmann, staring at his saturated radar display on the night of July 24, 1943, witnesses the beginning of this transformation. He does not know the aluminum strips have a name. He does not know the British feared using them for over a year. He only knows that his world, his training, his experience, his confident understanding of how the war is fought has changed fundamentally in the space of seconds. The green glow of his cathode ray tube, once a window into the night sky that revealed every approaching threat, has become a blizzard of false echoes. And in that moment, as thousands of bombers pass overhead, unimpeded by the defensive network that should have stopped them, the future of aerial warfare is written in aluminum and flame. The morning after the first Hamburg raid brings a peculiar silence to the radar stations. Technicians move through their procedures mechanically, checking equipment that functioned perfectly, but failed completely. In the wreckage scattered across northern Hamburg, recovery teams find not just the expected debris of high explosive and incendiary bombs, but something else entirely. Thousands upon thousands of metallic strips, glittering in the pale morning light like some bizarre metallic snowfall. The strips are collected methodically. Samples are photographed from multiple angles. Measurements are taken with precision instruments. The dimensions are recorded. 27 centimeters in length, 2 centimeters in width, with aluminum foil approximately 0.01 millimeters thick, bonded to black paper backing. The black paper serves a purpose beyond mere mounting. It provides weight, ensuring the strips fall slowly through the air rather than being blown about by wind currents. The slower descent rate means each strip remains in the air longer, creating radar returns for extended periods. Intelligence officers calculate the mathematics with growing dismay. Each bomber carried approximately 7 packages of these strips. Each package contained 2,200 individual strips. The packages were designed to open automatically when dropped, dispersing their contents across a wide area. 791 bombers, each dropping 1 package per minute for the duration of their approach and bombing run. The numbers are staggering. 15 million individual radar reflectors, each one optimized to return maximum signal at the precise frequency the Würzburg radar employs. The theoretical basis is elegant in its simplicity. Any conductor approximately half the wavelength of incident radio frequency energy will act as a resonant antenna. The Würzburg operates at 53 centimeter wavelength. Half of 53 centimeters is 26.5 centimeters. The British strips measure 27 centimeters. The match is not coincidental. British scientists clearly know the German radar frequencies with precision. When a radar pulse strikes one of these strips, the aluminum acts as a dipole antenna. The incoming electromagnetic energy induces electrical currents in the metal. These currents immediately re-radiate electromagnetic energy at the same frequency. The re-radiated energy travels back toward the radar receiver. On the display screen, this appears identical to a reflection from an aircraft. The radar cannot distinguish between energy reflected from a bomber's metal fuselage and energy re-radiated by a strip of aluminum foil. What makes the countermeasure devastatingly effective is not individual strip performance but collective behavior. One strip creates one radar return. 1,000 strips create 1,000 returns. 15 million strips create a display so saturated with contacts that identifying actual aircraft becomes impossible. It is like trying to find specific grains of sand on a beach by examining each grain individually. The task is theoretically possible, but practically impossible. Within the time constraints of combat operations, German scientists examining the strips recognize immediately that this represents more than tactical surprise. This represents a fundamental understanding of German radar technology. The British know the operating frequencies. They know the antenna characteristics. They know the signal processing methods. This level of knowledge suggests either highly effective intelligence gathering or parallel scientific development, or both. The implications extend beyond Hamburg. Every Würzburg radar in the German defensive network operates on similar frequencies within the ultra-high frequency band. The strips that blinded Hamburg's defenses will blind every other city's defenses equally well. The British have not just defeated Hamburg, they have defeated the entire system. In the days following the initial attack, Luftwaffe command struggles to formulate a response. The immediate reaction is to demand explanations from the radar operators. Were the sets functioning properly? Were the operators following correct procedures? Had maintenance been performed to specification? The answer to all these questions is yes. The equipment functioned exactly as designed. The operators followed their training precisely. The maintenance logs show no deficiencies. The problem is not equipment failure or operator error. The problem is that the fundamental physical principle upon which radar operates has been exploited by an adversary who understands that principle as thoroughly as German engineers do. You cannot train your way out of physics. You cannot improve maintenance procedures to defeat electromagnetic theory. You must develop new technology or new tactics, and both require time that Hamburg's defenders do not have. On July 27th, just 3 days after the first attack, RAF Bomber Command returns. The intelligence reports reaching radar stations before the raid are unambiguous. Expect the same jamming. Expect the same saturation. Expect the same blindness. At 10 minutes past midnight, the early warning radars detect the incoming stream. At 37 minutes past midnight, Klaus Hoffmann's display erupts with returns again. The mass of contacts is, if anything, denser than the first raid. The British are using more strips, or distributing them more effectively, or both. This time, there is no confusion. Every operator knows what is happening. Every controller understands the limitations they face. The fighters are launched anyway because doing nothing is not an option. Some manage visual interceptions, attacking bombers silhouetted against the fires below. But these are isolated engagements, individual successes in a larger failure. The coordinated, radar-directed precision that defined German night fighter tactics has been replaced by random encounters that depend more on luck than skill. The bombs fall for 2 hours. The damage from this second raid exceeds the first by an order of magnitude. The meteorological conditions combine with the density of incendiary bombs to create something unprecedented in the history of warfare. A firestorm. The fires become so intense they create their own weather system. Superheated air rises rapidly, drawing in surrounding air at ground level. Winds of 240 kilometers per hour rush inward toward the burning districts. The temperature at street level reaches 800 degrees Celsius, hot enough to ignite wood and fabric spontaneously without direct flame contact. People seeking shelter in basements suffocate as the firestorm consumes all available oxygen. Others attempting to flee are caught in the hurricane-force winds and pulled into the flames. The asphalt in the streets melts, trapping people trying to run. Bodies are found later reduced to ash and bone, clustered in places where they sought shelter that proved no protection against this intensity of heat. The death toll from this single night approaches 20,000 people. Most die not from direct bomb hits but from the firestorm that follows. The bombing creates the conditions, the fire creates the catastrophe, and German radar, blinded by aluminum strips, prevented none of it. In subsequent days, 2 more major raids strike Hamburg. Each time the jamming is employed. Each time German radar is rendered ineffective. By the time Operation Gomorrah concludes, Hamburg has sustained damage that eclipses anything previously seen in the bombing campaign. Over 40,000 people are dead. 60% of the city's housing is destroyed or severely damaged. More than 1 million people, approximately half the city's population, have evacuated to other areas. The industrial damage is substantial, but not crippling. The shipyards, though damaged, remain operational. Submarine production continues, though at reduced rates. The aircraft engine factories are hit but not destroyed. German industry proves remarkably resilient, capable of dispersing production and rebuilding damaged facilities with impressive speed. But the psychological impact cannot be so easily repaired. Hamburg was Germany's second largest city, a major port, a significant industrial center. If Hamburg could be devastated this thoroughly, no German city was safe. The promise of the defensive radar network, the assurance that German technology could protect German cities, had been exposed as illusory. For the men operating the radar stations, the experience is professionally humiliating and personally terrifying. They are trained specialists, experts in sophisticated technology, practitioners of a technical art that requires months of education and hundreds of hours of practice. Yet they sit helpless at their controls while enemy bombers destroy the cities they are supposed to defend. The technology still works, the equipment still functions, but the advantage has shifted to the enemy, and all their expertise cannot recover it. Klaus Hoffmann's experience during these raids is representative of thousands of operators across Germany. Each night, he powers up his Würzburg, checks his systems, confirms all indicators show proper operation. Each night, when the British arrive, his display becomes useless. Each night, he listens to the bombs falling and knows his equipment, his training, his dedication make no difference. The psychological toll of this helplessness is significant. Some operators request transfer to other duties, preferring to face danger where their actions might have effect, rather than sit at displays showing information they cannot use. Others become fatalistic, performing their duties mechanically while recognizing the futility. A few maintain optimism, believing that German engineering will develop countermeasures that restore their capability. The countermeasures do come, though not quickly enough to prevent the devastation of Hamburg. The first modification, based on Doppler shift detection, begins reaching operational units in late August. The modification requires adding components to the existing Würzburg hardware and training operators in new display interpretation techniques. The theory is sound. Aircraft moving at 300 km per hour or more produce measurable Doppler shifts in the reflected radar energy. Aluminum strips falling at 20 km per hour produce minimal shift. By adding a stable local oscillator and frequency comparison circuitry, the modified Würzburg can measure the Doppler shift of each return. The display is modified to show returns color-coded or intensity modulated based on their Doppler characteristics. High-velocity returns, likely aircraft, appear bright. Low-velocity returns, likely chaff, appear dim or are suppressed entirely. In practice, the modification works imperfectly. The added circuitry reduces the radar's effective detection range by approximately 30%. The frequency comparison circuits are sensitive to temperature variations and require constant calibration. The display modifications create interpretation challenges. Operators trained for months on the original displays must relearn pattern recognition on the modified systems. Most critically, the modification cannot completely eliminate chaff returns. It can only reduce their prominence relative to aircraft returns. An experienced operator using a modified Würzburg can track aircraft through moderate jamming. But the British are not employing moderate jamming. They are saturating entire defensive sectors with millions of reflectors. Even with Doppler filtering, the displays remain cluttered. The modification improves the situation, but does not solve it. Alternative approaches are pursued simultaneously. A system using mechanical propeller modulators attempts to distinguish between stable aircraft returns and fluctuating chaff returns. The logic is that chaff strips tumbling through the air will produce returns that vary rapidly in amplitude as their orientation changes. Aircraft maintaining steady flight will produce returns of more consistent amplitude. This approach shows promise in testing but proves difficult to implement operationally. The modulator mechanisms are mechanically complex and prone to failure. The signal processing required to analyze return amplitude variations exceeds the capability of the analog electronics available. A few specially modified sets are deployed to expert operators, and these achieve some success. But the system cannot be mass-produced quickly enough or made reliable enough for general deployment. The frequency switching approach offers another possibility. If the British have cut their chaff strips to precisely match the Würzburg's frequency, then changing the frequency should render the chaff ineffective. The Würzburg's frequency band is expanded through modifications to the transmitter and receiver circuits. Instead of operating at a single fixed frequency, the modified sets can operate at any frequency within a range spanning more than 100 MHz. Multiple frequency bands are defined, each approximately 10 MHz wide. Operators can switch between bands during operations. If chaff jamming appears at one frequency, switch to another. The British cannot carry chaff cut for every possible frequency. They must choose which frequencies to jam, and if the Germans switch to an unjammed frequency, they regain their capability. This approach works temporarily. During raids in autumn 1943, German operators report periods where switching frequencies allows them to track through the jamming, but the advantage is short-lived. British intelligence monitors German radar transmissions and notes the new frequencies being employed. Within weeks, chaff cut for the new frequencies appears in RAF chaff dispensers. The Germans switch frequencies. The British add those frequencies to their jamming. Back and forth, measure and countermeasure.